Today we are looking at partial derivatives and gradients. Our learning objectives are to understand what partial derivatives are, understand what the gradient of a function is, compute some partial derivatives, and then compute some gradients of some functions. So what are partial derivatives? So partial derivatives measure the rate of change with respect to one variable at a time, and they hold all other variables constant. So the notation of partial derivatives, if we had derivative with respect to x, we would have the notion as this with this curly symbol, and if it was respect to y, we would have this, and then if it was z, then this y would change into a z. So we use partial derivatives when we have a function of multiple variables so that we can just focus on one variable at a time. So for example, if we had the function x squared y plus 3x y squared, this is an example of a function with multiple variables. In this case, it has two variables, x and y. If we were to work out the partial derivative with respect to x, we would look at this function and treat the y's as constants. So the y's are just numbers, and we would go about differentiating it. So when we differentiate with respect to x, we look at this x, and when we differentiate that, it will just be 2x, and then we'll just attach that y. And then the same thing over here. In this case, we have 3x over here. When we differentiate the 3x, we just get 3, so we're left with 3y squared. And then if we do the same thing, but with respect to y, we would treat all the x's as constants now. So differentiating y is just 1, so we get x squared. And over here, differentiating y squared will give us 2y, so we end up with 6xy. So this function over here would be a 3D surface, as we could write this as z is equal to f, the function of x and y, which is z is equal to x squared y plus 3x y squared. So this is some kind of three-dimensional graph. And so what this is telling us when we partially differentiate with respect to x is the slope if you move in the x direction. And what this is telling you is the slope if you move in the y direction. So this is quite important when we look at the gradient vector. So the notation for the gradient vector is delta and then f, or the function, which is equal to the partial derivative with respect to x, and then the partial derivative with respect to y. So that would be, for a function like this, if we had 3 variables in the function, it would look something like this. So this is for a function with 2 variables, this is a function with 3 variables. And what this gradient vector tells us is, or what its meaning is it points in the direction of steepest increase of the gradient. And the magnitude of this vector is how steep the increase is. Okay, just very quickly, if we go back to this function, the gradient vector for this function would simply just be 2x y plus 3y squared, comma, x squared plus 6xy. So that would be the gradient vector of this function. What we also can do with partial derivatives is find higher order partial derivatives. So we could partially differentiate this again with respect to x. So if we have a look at that, when we differentiate partially with respect to x once, we get 2xy plus 3y squared. Differentiating partially again with respect to x gives us just 2y, because this is just a constant as there's no x terms. If we do the same thing for when we differentiated partially with respect to y, we had x squared plus 6xy. When we partially differentiate this again, it becomes just 6x, as this is just a constant. And when we differentiate the 6y, we just are left behind with 6x. What we also can do with this is look at how the rate of change of f with respect to y changes as x changes. So the notation for that would look like this. So in order to work this out, what we first need to do is take the partial derivative with respect to y, which is what we've done over here. Then we now differentiate with respect to x. So we look at this and we differentiate with respect to x. So we get 2x plus 6y. And this is just called a mixed partial. And if we look over here, we can do the exact same thing. And so we get 2x plus 6y. And what we should notice is that these two should always be the same. If they're not the same, it just means that you've done something wrong. Going back to the gradient vector, like I said before, the direction, it points in the direction of steepest increase, and the magnitude of this vector shows how steep that increase is. If we think about this intuitively, like I said before, this would be some sort of three-dimensional graph. And what this gradient vector does is, if you are somewhere on this graph, this vector will point in the direction of where the function increases fastest. Okay, cool. If we now look at computing these partial derivatives, we will start off with a Lagrangian, which is going to be pretty difficult. If we first differentiate this partially with respect to x, we will have to use product rule for this, and so we get e to the power of y over x plus x e to the power of y over x multiplied by this differentiated, which is minus y over x squared. So in order to differentiate this, we're just doing y and then x to the power of minus 1, and we're just ignoring the y, keeping it as a constant, and differentiating x. And so we get this. If we now differentiate this, we will get just 1 over x, and then differentiating this x will just leave behind minus lambda. Doing the same thing for y, we get x e to the power of y over x multiplied by 1 over x plus 1 over y minus 2 lambda. And so if we simplified this, we would get e to the power of 1 over x, e to the power of y over x plus 1 over y minus 2 lambda. And if we just factorize out e to the power of y over x, we get 1 plus 1 minus y over x plus 1 over x minus lambda. Cool. If we look at another function, let's say we had x squared plus y squared all to the power of 3 multiplied by ln xy. Differentiating this partially with respect to x will give us 6x x squared plus y squared to the power of 2. So I'm using chain rule for this, dropping down the power and then minusing 1 from the power over here. So when I drop down the power, we get 3. And then we need to differentiate what's inside. We're treating y squared as a constant, so we're just differentiating the x squared, which will be 2x. So 3 times 2x will be 6x. And then we're just going to multiply ln xy onto here. Then because we're using product rule, we do plus x squared plus y squared to the power of 3, this differentiated, which is just 1 over x. If we now partially differentiate with respect to y, we get 6y x squared plus y squared to the power of 2, and then ln xy stays the same, and then plus x squared plus y squared to the power of 3 multiplied by 1 over y. Cool, so pretty straightforward. Okay, let's say we had a gradient vector which was 2x, 2y, and we had to draw the flow of this vector, or the stream plot. In order to do this, what we can do is look at some random points. For example, if we had 0, 0, this vector would churn out 0, 0. If we had 1, 0, this vector would churn out 2, 0. If we had 0, 1, this would churn out 0, 2. Cool. We would get this overall pattern. So if this was our graph, 0, 0 maps onto 0, 0, 1, 0 maps onto 2, 0. So we get an arrow going like that. And then that's the same over here, same thing happening over here, and then same thing happening over here. If we then had a point over here, that would map something like that, and the same over here, and the same over here. So essentially, we get a stream plot where the gradient flow is just away from the origin. If we had the gradient y comma x, so if we had the point 0, 0, it would churn out 0, 0. If we had 1, 0, it would churn out 0, 1. If it had 0, 1, it would churn out 1, 0. If we had minus 1, 0, it would churn out 0, minus 1. If it had 0, minus 1, it would churn out minus 1, 0. And then if we had any points on the line y is equal to x, it would just churn out the same thing. For example, 5, 5 stays the same as 5, 5. 4, 4 stays the same. 3, 3 stays the same. 9, 9 stays the same. So when we end up drawing this, we'll see that 0.00 stays the same. 1, 0 tries to become 0, 1. Okay, cool. Hopefully that all made sense, and you've gained a deeper understanding on partial derivatives and gradients.